We'll look now at a very famous mathematical formula. It's called the quadratic formula. So called because it gives us a way of solving quadratic polynomials or second-order polynomials. Right, so again, the quadratic here is referring to second-order polynomials. So what does this formula allow us to do? Well, it allows us to solve equations that look like the following. 0 equals ax squared plus bx plus c. So this is a generic second-order polynomial. And what our formula says is kind of remarkable. It says that all I need to do to be able to solve this is plug my coefficients into this formula. So take a, b, and c and run them in the following formula. The solutions are going to be x equals minus b plus or minus, this is important, square root of b squared minus 4ac, and then I divide everything by 2a. So the plus minus here says one solution will look like negative b minus square root of b squared minus 4ac over 2a. And another solution, so I'll call this x1, I get another solution, x2, given by negative b plus square root of b squared minus 4ac over 2a. So that plus minus tells me that in almost all situations, I don't just get one solution, I get two. One corresponding to the negative branch, one corresponding to the positive branch. Now there is sort of an exceptional case in which you only get one solution. And it's when this plus minus doesn't matter, because what comes after it is 0. That is, when square root of b squared minus 4ac is equal to 0, I only get one solution. So we give a special name for this quantity that determines that. So this b squared minus 4ac is called the discriminant, which is a useful term to know for the CLEP. Sometimes they ask about this. So it discriminates between two cases. Case 1, I'll call it, and case 2. So case 1 will be one solution. Case 2 will be two solutions. As long as b squared minus 4ac is not 0, you'll get two solutions. If it's 0, you only get one. So let's look at a few examples of second-order polynomials and using the quadratic formula. So here I have x squared minus 7x plus 9. All I need to do to solve this is to run these coefficients in the formula. So it's helpful, at least when you're beginning, eventually you get good enough to not have to do this, to write out what the coefficients are so that the substitution into the formula is more straightforward. So let's see what a, b, and c are. So a is the coefficient on x squared, which is 1 in this case. If you don't see a coefficient, it's because the coefficient's 1, and multiplying by 1 does nothing. b is minus 7, that's the coefficient here, and c is equal to 9. And now all we have to do is plug into the formula. So I know that x equals negative b, so negative negative 7, plus or minus square root of minus 7 squared, minus 4 times a is 1, c is 9. Right, and now all I'll do is I'll simplify this out, and we'll get hopefully a nice solution, maybe not so nice. So this is negative negative 7 is positive 7, because the negatives cancel, plus or minus square root of 49, minus 4 times 9 is 36, divided by 2, and then 49 minus 36 is 13, of course, divided by 2. And there's actually nothing else we can really do with this, because square root of 13 does not simplify any further. It does not contain a perfect square. So I'll say square root of 13 cannot be simplified. And I'll say this is because it has no perfect square factors. If you don't know what that means, it's not really very important for the CLEP, but it is sort of interesting in its own right. Okay. So let's move on to a second example. Now in this case, we have actually a leading coefficient other than 1. Right? So the coefficient on x squared for these is sometimes called the leading coefficient. Leading because it's the coefficient on the highest order term. In the previous example, it was 1. Here it's 2. But we'll play the same game. We'll write out what each of the coefficients are, and then we'll plug into the formula. So in this case, a is equal to 2, b is equal to 1, and c is equal to negative 3. Okay, so then x is equal to negative b, so negative 1, plus or minus b squared is 1 squared, minus 4 times a, which is 2, times c, which is minus 3, divided by 2 times a, which is 2 now. So a lot of times these polynomials are what you would call monic, which means that the leading coefficient is 1. In this case, it's not. So you do have to do something in the denominator. It's not 2 times 1, it's 2 times 2. But now we're going to do the same thing as before. We are going to simplify each of the individual pieces in the formula and see what pops out. So let's take a look inside of the square root sign. So 1 squared is 1. 4 times 2 times minus 3 is, let's see here, positive 24. And then 2 times 2 is 4. So do a little more simplification under the square root sign. 1 plus 24 is 25. Divided by 4. Let's continue over here. And then it's good to remember sort of your what are called perfect squares. So things that have square roots, when I take the square root, I get an integer back, a whole number. So in this case, we know that square root of 25 is 5, and then I divide by 4. Okay? So, and you could leave it like this. You could also split it up and say, well, I get minus 1 plus 5 over 4. And minus 1 minus 5 over 4. So I get 1 and then negative 3 halves. Or you can leave it like this. So again, we get two solutions in this case. And in fact, one of them is positive, one of them is negative. That's not always the case. Sometimes it does happen that they're both positive or both negative, but it is possible that you get one of each.